Number 4, it's applied max and min problems. So I would relate this to those related rate problems. Okay, that similar type of level, that similar type of a lot of work to do. One of the most important applications of derivatives curves is optimizing things. That's what people use derivatives a lot for like higher, like my wife uses some of these actually when she's looking at research and she's doing some stuff on muscle tissue. Like you'll optimize in terms of what the max or min like force rate you want to be looking at. I mean, really complex things come into play, and this actually, like I said, we're not just doing this. It's not just math like the quadratic formula you're just doing has really no outcome. Sometimes this actually plays a key role in doing a lot of things that we use on a day-to-day basis. Now it's complicated, but it is how we optimize and maximize max or min certain situations. We're going to start with basics, and then we're going to actually have a couple of problems that are somewhat applied. Okay, you may not care about trying to optimize cost of not putting a wire underwater versus over the ground, but we're going to do that anyway. Okay, all right. So first example is kind of a more simple, like a math example. Find two positive numbers whose product is 10,000 and whose sum is a minimum. Okay. Find two positive numbers whose product is 10,000 and whose sum is a minimum. Okay. So first thing I want to do is we want to write out the two things that we're given. We are given two positive numbers. Okay. So we're doing, okay, these two positive numbers, x and y, two different numbers. And their product is 10,000. That's what we know so far. So in order to do these, the first thing you want to do, and we're going to do two examples. I'm going to give you a kind of steps to solve type of thing, or steps to look for. But you want to have everything in one variable. So for example, this is the equation right here. This is what we're trying to max or minimize. Does that make sense? We want the minimum numbers they would add together. Because it says find the two positive numbers whose product is 10,000 and whose sum is a minimum. So we're minimizing this. That's what we're minimizing. But we want to do that. In order to do that, if we want to take the derivative of that, we would like to have them all in the same variable. Alas, that's why we have the second thing. The second thing, I can solve for y and get it terms of x by simply just doing this. Now I know what y is in terms of x. Now I can put this here, and we no longer have two variables. Questions about that? So I'm going to go ahead and do that while you're writing that down. So we should have s equals x plus 10,000 over x. Now we have that sum in terms of one variable. Okay? All right. Now what? What would you do next? Yeah, derivative, right? Or max and min, that's the whole unit. Take the derivative, find the critical points, right? Find the derivative, get the critical point. So we're taking the derivative, want s prime. 1, derivative of x is 1, plus, that's an x of negative 1. So we're dropping a negative 1, which makes this negative. And then it's just going to be 10,000 over x squared. Okay? Because it went from negative 1 to negative 2, right? So there it is. Now, we did one kind of like this yesterday in the sense of we don't like it when they're not together because we can't see the zeros simply. Okay, what I'm saying is we want to get this all one fraction so we can see where our zeros and our D and E's are. Okay, when you have the 1 there, it's kind of a guessing game. Like I can go and figure out, well, what squared's 10,000? I can do that. Okay, but it's a little bit easier if I can put them together. To put them together, it's not too hard. To make this common denominator, it's just going to be x squared over x squared. Okay, and now we have it in one fraction. Okay, and one thing that it says in the beginning that I didn't really write down, but we only care about x's that are what? And y's. Positive, right? Because it says two positive numbers. So we don't care about negatives. Just keep that in mind. Okay, if I factor the top, that is the difference of squares. We're going to be at x plus 100, x minus 100. Yep. Because this right here is a negative 1. So when I do the derivative of a negative 1, it drops a negative. So it's kind of skip that step. Okay, good question. Okay, all over x squared. So my critical values are negative 100, 100, and 0. But we don't care about negative 100, right? What's that? Do we care about 0? Is 0 positive? What's that? Is it positive, Nikita? Okay, so we care about 0.
But if you put x greater than 0,
Yeah. That's what I'm thinking as well. So hold on. You're right. I'm getting to that. So we have 100 is the only one that we want because 0 is technically not going to be positive or negative. 0 is in the middle. So we only care about 100 in terms of our critical value. Another reason we only care about 100 is because 0 is a critical value in the sense that it's the starting point, but the starting point can't be my min. Right? Because we don't know what's on the other side. We don't know if it's increasing or decreasing over there. So 0 is not going to yield us a max or min value. We're only expecting a what? A min. It wants us to find the minimum. We have one critical value. We're hoping that's going to be a minimum. Does that make sense? Okay? So 100 is the only critical value we're actually going to look at. So quickly what we can do is we just want to look at 99 and like 101, just two numbers around 100 and see what's happening. Okay, and that's into my derivative. Okay, into this. Because that'll give me if it's a positive or negative tangent slope. That'll tell me increasing, decreasing. Okay, so 100 is what we're looking at. So essentially what we're doing is we just have this chart here of 100 is all. We're trying a left side, we're trying a right side. Okay, 99, I'm going to put 99 in. I don't have the number I got, but I got decreasing. And I put 101, I got increasing, which is what we wanted. It decreases to 100 and comes up. So what we kind of prove, which is actually ended up being just kind of, I don't want to say obvious, but it's 100, x is 100, and y is 100, is your values of the two numbers. They actually end up being the same value. 100 times 100 is 10,000. 100 plus 100 is 200. That yields the minimum. Oh, yeah, it's right here. Right here, we know x and y is 10,000. So if I put 100 in for x, I divide 10,000 by x, and I get what y is. So we know by our critical values, this tells us at what point the min or max is. We plug this in for x, so essentially I put it right here. 10,000 divided by 100 is 100 again. So the point is 100, 100. Okay? So what is the actual sum that is the minimum? 200. 100 plus 100. We got the point from here. We plugged it into here. So 200 is the minimum sum possible to get 10,000. Any questions there? Okay. Let's try another one here, a little bit more applied. We'll have 2 pages for it, and then we'll go through the steps. All right. So I kind of gave the start in the picture here, but if 2,700 square centimeters of material is available to make a box with a square base and an open top, find the largest possible volume of the box. So it tells you how much material you have, and you want to make the biggest box possible. So what are we maximizing? The volume, right? We want to maximize the volume of that box, make the biggest box possible. Okay. So let x be the length of the box. So we know it's x by x because it's a square base. We know this is the height, just h. We don't know what the height is. Okay, this is what's going to happen quite often in these problems. You're going to have 2 variables. Again, we're going to want to get in terms of 1. We'll work on that. Okay. All right. So first thing we want to know is we want to know it's a square base. So we know being a square base, that gives us that the base is essentially is x squared. The area of the base is. We know its height is h. So that would be the volume. So that's what this is here, x squared times h. That's how they got that. Then we also, since we have these variables and we know we have surface area is something else we can compare to, the surface area, we want to pay attention to it's an open top box, so we do not have 2x squared, we have 1x squared. We just have this one. And then we have 4 xh's. Okay, let me say that again. This box here is x squared on the bottom. It's an open top, so we don't have 2x squared. It has 1 of them. The rectangles around it are x's times h's. So it's 4 of those. Why did I do surface area? Why is that important? Just to compare to something, or? 4xh. Oh, yeah, that's definitely not an h. I have bad handwriting, but that's not close. All right, 4xh. 4x4. I'm going to go 4 by 4, I guess. Okay, 4xh. So the reason being, a lot of you guys kind of pointing at it, but we're pretty scared right now because I told you it's going to be hard. This tells you how much material you have. Material is the surface you can use. So 2,700 is the amount of surface area I'm allowed to use. That's the maximum I can use. That's all I have. Does that make sense? Okay. All right. So I'm going to set this equal to 2,700. Now, why is that important? Let's take a step back further. What are we trying to maximize or minimize? Let's go back to the original question I started with the problem with. Volume, correct. So then we want volume to be all in what? One variable, correct. We have surface area now with a value, just like the 10,000 from the previous problem. So now we can get our h by itself to get rid of it from the volume side. Let me say that one more time. By having this value, we now can move the x squared, divide the 4x, and isolate h. So we take this and put it in for there, so there's no longer an h. So you're given this in the beginning in order to help you isolate or get rid of a variable. It's kind of like I don't want to say comparison, but it gives you something to, it gives you something to compare it to. So the work we're going to do now is I'm going to minus x squared. We're solving for h right now to sub it in for this h. That's what we're doing. Because remember, this is the guy we're maximizing. We want to maximize the volume of the box. Okay? All right. So let's get that here. So it's 2,700 minus x squared divided by 4x. That's what h is. And then we're going to sub it in. I'll sub it in the next page. So get that down. I'll wait for you. I'll pause the video. And then we'll start the next page with that. I want to make sure we get to this lesson here. So we're going to sub that in. So I subbed it in. Now we're going to simplify. You multiply the x squared to the top, right, because it's over 1. So then it's going to be 2700 x squared minus x to the 4th over 4x. I can hack an x off of all of them. They all have an x. So then it's going to be 2700x minus x cubed all over 4. The reason I like to do that is now I don't have to do quotient rule, right? Okay, we got rid of that x, now we don't have to do quotient rule. We can just go ahead and do the derivative here. So we'll do the derivative next. After yeah. It's weird. I wonder why I did that. Interesting. We'll come back to that. I'm not sure why I did that, but let's just go on to find the derivative. So when you do the derivative, you can write. It might help to write these in 2 pieces. Might help to do that just so you kind of see what you're taking the derivative of in your 2 pieces. So you can see when I do the derivative, my v prime will be x. Sorry, not x. I said the wrong thing. 2700 over 4. What is that? You guys, or I have that here. It's 675. So the x is gone, right? This is all that's left. That's 675. Drop the 3, 3/4 x squared. Yep.
Why wouldn't you do low d high minus high d low?
Because the bottom is not have a variable. So the bottom, you only have to do low d high versus high d low if the derivative of what you're doing on the bottom. Because derivative of so if you did do, no, it's a good question. If you did do the quotient rule, what's the derivative of low? So you don't need to do it. Okay. No, actually, it would still work. Yeah, it just you'd be left with this. Yeah. Because you do. Well, no, because you're over low squared. No, low squared 16. Yeah, no, it should still work. Okay. All right, so that's that. So now we want to go ahead and look at what are the critical values. So we essentially just need to solve this. So this is a situation where I don't really have a fraction or a variable on the bottom. So I'm just going to solve this like a normal math problem. I'm going to minus 675. I'm going to divide by 3/4, and I'm going to square root. Because we're solving for the 0. At the end of the day, your critical numbers are the zeros, or what makes it not exist. We don't have any of those problems here, just the 0. So we're going to do this, and we're just going to solve it with algebra here. So we're going to minus, because remember, 0 is a critical number. That's what we do on those things from before. We're figuring out what makes it 0. So we're figuring out algebra-wise what makes it 0 by just solving. Because before we've been dealing with the fractions, right? Zeros up here make a 0. Zeros down here make D and E. This is just a straight problem. We're trying to figure out what makes that 0. There's no fractions. So essentially, like, you can just make a note. We're trying to find the 0. That's what we're always doing. Okay? Negative 3/4 x squared. Divide by negative 3/4. Divide by negative 3/4. That gives you 900, which we like because 900 is a perfect square, plus or minus 30. Now, why do I not care about the minus? Right, we're doing lengths of a box, right? So the negative's irrelevant. So 30 is what my x is going to be, okay, to maximize that box. Oh, okay, I know why we did that earlier. Okay, so we have from before. All right, hold on 1 second. Back to what we were doing here. We're done. I'm glad I confused you at the end. But like I said, we don't care about the negative 30 because it's length. So 30 is what we're expecting to be our max or min. So we can check that by putting this into, put in 31 into here, and then we can put in 29 into here. It should be increasing to decreasing, right? Because we're expecting a max. Okay, so if you do that, that's what will happen. This is your maximum. Whoops, eraser. Okay, so that's my max value. So if that's my max, if you're saying, well, I have my x, that means my square base is 30 by 30. What's the h? How do we find the h? Yeah, we plug the 30 into this guy. H is by itself. Put 30 in here, and you'll get your h. Okay. 900. Can somebody do that for me? 2,700 minus 900, 1,800. 1,800 divided by, is that 1,200? What is it? 15? Okay. So then we have 30 by 30 by 15. So that max volume, can Janae, can you do it? 30 times 15 is? I'll make sure it matches my number here.
13,500.
Yep. Okay. So the max volume is 13,500 cubic centimeters. Okay, good. Perfect. All right, so you get a little short kind of break here, well, in terms of me doing a problem. Here's the steps they suggest to do these type of problems. I'll pause the video on this, but you can pause it if you're watching the video and write them down, or if they're in your book. But so think about these things as you kind of briefly looked at them for number 3, and let's see if we can come up with what it's asking us to do. Okay, so here's the question. Good news, it's parabolas. Math 20, no problem, right? Parabolas are easy. Standard form, no big deal. You guys should be able to graph 6 minus x squared without even looking. It should be easy, right? 1, 2, 3, 4, 5, 6, down. That's all it looks like. Okay, anyway, find the points of the parabola 6 minus x squared that are the closest to the point 0, 3. What's it asking me to do? What's it asking us to do? Yeah. Think in terms of, Janae, think in terms of maxing and minimizing. What's it asking us to do? What's that? So here's 0, 3, right? So this is what it's asking us to do. It's asking us to figure out which, I don't know where, but it's going to be the same because they're symmetric. What are the 2 closest points to this point? Is it straight across? Is it down? But again, what are we maximizing or minimizing? Before it was volume, right? Before that, it was the numbers. We were trying to minimize the sum. What are we trying to, I'm going to tell you, we're trying to minimize. What are we trying to minimize? Distance. We're trying to minimize distance. Okay, we know what distance formula is. Okay, you hopefully do. So remember distance formula. So we don't know, so that's why I have x and y's in there. I have minus 0, because remember distance is, we're trying to do distance from 0, 3. So x minus 0, because that's my x coordinate, y minus 3, because that's my y coordinate. That's the distance formula. If you didn't know that, remember it's x1 minus x2 squared plus y minus 1 y2 squared, all square rooted. So let's just compare this to the last problem. This distance is my volume, right? What do we do next to that equation? What did we do next? Got one variable. Good. Can I do that here? Do we know what y is? It's that. So just put that in right there. Minus a 3. I'm going to go ahead and put those like terms together. So 6 minus x squared minus 3 is 3 minus x squared. Squared. So this is where it gets a bit tricky. It's a stinking radical. We always hate radicals. Nobody likes radicals. I don't. Hate teaching them.
So 6 minus x squared minus 3 all squared simplifies to that.
Yes. Yeah, the zeros are relevant, correct. It's just x squared. I'll do that now. Good point, M. Didn't work. All right. So we also have an x squared. Okay. So we're actually going to square both sides. So you're like, well, what's d squared mean? Good point. We're going to talk about that. So we're going to square both sides so that we have d squared equals x squared plus 3 minus x squared squared. The reason being is now we can go ahead and FOIL that out, kind of get our things together. Okay? You see what I'm saying? I'm going to FOIL this out. So I'm going to go x squared plus 9 minus 6x squared plus x4. Everybody see that FOIL there? Okay. Combine our like terms. So that's where we're at. Okay. Okay. We are going to take the derivative still. So even though that was d squared, right? We still know that we're still taking the derivative and we're still maximizing. The reason it's becoming d squared is does anyone want to take like an educated guess of why it's become that? Yeah, we're thinking about two answers, exactly. And so what's happening is we're kind of operating on the idea that we're expecting two answers. Now, we still have the derivative, so this still is the derivative. We may not know what this over here is, because that's why I just told you, is that we're expecting two answers of what this is telling us. But we still would do what at this point? Just forget we don't know what that is. What would we do after the derivative? Critical points. That's still what we want to do. Okay, so we would pull out a what? X, 2x. And we have x squared minus 5. So, is that right? No, that's right. Oh, yeah, 2. Oh, yeah. Thank you. Okay, and so then what we have is we have a critical point of 0. What's this one? You guys can do that in your head? Add the 5, divide the 2, square root it. So square root of 2.5 or 5/2, plus or minus. So there's my 3 critical points. 0 plus square root 2.5 minus root 2.5. So 0 is not helpful because why? What's that? Sorry, I didn't hear you. Has to be a distance. Okay, well, but 0 represents the x value because, right, these are coordinates. So it could be helpful, but that would mean that they're saying that this is the closest. So our critical points that we have to look at, we're looking at negative root 2.5. Can somebody tell me what approximate that is? That's probably going to be like 1 point something.
1.58.
Okay, 1.58. So right about here, oh, that's pretty dang close. These are the 2 points that we're looking at, and this is the point we're looking at to see which is the closest distance from there. How can I do that? Where would I plug it in back to? The distance formula, correct. So we are going to take, if I plug 0 into here, but we need to get 0, I have to get the y values associated with them, right? Because this is in terms of x and y. So 0 is at where? What's the point 0 on the original graph? 0, 6, good. So 0, 6 is what I would put in here and try. Okay, go ahead and do that. Tell me for your distance. And then can somebody, so 2.5, that would be 6 minus 2.5, so I'd have, the other one would be root 2.5, and 6 minus that would be 3.5. And then the negative would be the same thing. All right, so we need to try these three in the distance and see which one has the shortest distance. These two, I hope you understand, they're mirrored. They're going to be the same. Right? They're mirrored when you plug these in. What's that? The 3.5? I did it in my head. If you square x squared, so if you square that, you get the square root goes away. 6 minus 2.5 is 3. To get the point. Yeah, to get the point, I put those there. Now I can put these into here, into the distance formula. Okay, I'll pause the video for a second. Do you have questions? Yes, it's going to be 2 points, right? Because it says find the points. And being a parabola, it's symmetric, so it's going to have those 2 points. Yep. So the 2 points we got is root 2.5 and negative root 2.5 at 3.5. Okay, we got that from our critical points, plugging them in. 0 ended up being a maximum. Okay, all right.